All right, then let's move on with the last bit of this session and talk a little bit about data preparation. Arguably, we did it all the time. Now I want to focus on some more concrete recipes, what you should do or what you should look into as part of the analytics process when you work with data, when you work on the assignment task, for example. That's sort of the setting. Right, so this is what I believe can count as a model, a process model of the individual steps, the activities in data preparation. We have selections as before in the process model, cleaning, transformation, reduction. There are some minor differences. Cleaning and transformation you saw before in the analytics process. I added reduction here. My goal is to identify some common activities in data prep and also their order. Although, when speaking about order, it is important to note that the individual steps that are taken in data preparation, and as they are depicted here, they are typically not necessarily followed in a sequential manner. Let's start from cleaning. Once you have your data set, you clean it. You look into issues of noise, missing values, and outliers. Afterwards, you enter the transformation stage. It is not entirely impossible that at this point I realize that you need to go back to do some more cleaning. So don't overinterpret the errors. This is all I'm saying here, right? And other than that, you can take this slide as a map that will accompany you throughout the remainder of this chapter. The tasks that you see here in the greenish boxes, noise, missing value, outliers. So I take these as tasks: scaling, discretization, category coding. These are tasks, and several of these I want to elaborate on in the remainder. Some others, feature engineering, feature selection, for example, they will come later in the course. So don't be surprised if you will not observe a perfect match between the bullets that you see here and later chapters. Some will come later, that is by design. But let's move on. Data cleaning. So in a nutshell, we have to deal with noise in the data, missing values and outliers. And in my example on the right hand side, I am trying to sketch what these are. Missing values, no information available. We have a data set with a target, bad, so I'm once again in the space of credit scoring. Bad means a bad payer, customer not paying back a loan. And as covariates, we see date of birth and salary, just examples, and one value for customer number 6, date of birth, is unavailable, a missing value. And if you look more closely, you see another value. It's highlighted, so you don't need to look that closely, really. A date of birth that clearly is an error, right? And because it clearly is an error, the type of recipe is clear insofar as this point cannot be real. Either we have a way to correct the error. Normally we have not correct the error. We would need to go back to the data owner, or ideally those who were capturing that data. Maybe there is a way to go to marketing or sales and trying to identify, so who's actually this person, customer number 9, who is that? And then maybe there is a way to correct the error. Very often this will not be the case, and then we can just delete the value and treat this as missing value. And well, then worry about strategies to handle missing values. And lastly, salary. Let's look at salary. You immediately spot the single outlier I put there. One value that is really large, really nice salary, but just from the value, we could not tell whether this is an actual salary or whether this is a data error. With age, we can be sure. Nobody living these days was born in 1789, that is clear. probably a typo and it was meant to read as 1989. That we would then need to check. But this value can't be true. Whereas this salary, it's quite possible, right? So here the question is, how do we deal with this outlier? Do we leave it as is? That's strategy number 1. Or do we adjust it? That's strategy number 2. Adjustment means we manipulate our data. That might sound a bit odd. Manipulating the data, really? Although it is an actual value. Let's assume it's just an actual true income value. Yes, indeed, for the purpose of analytical modeling, it might be preferable to manipulate the data to change some values to artificially lower this salary, because its impact on your model might be substantial. And depending what your model is aimed to do, you might want to avoid such a big impact of a single observation, right? So this is basically the key 3 issues in data cleaning: missing values, errors, and outliers. And we already identified some potential remedies or strategies. So just to recapitalize, for errors, correct if feasible, otherwise we treat them as missing, so that's quite simple. For missing values, well, we can keep them or we can delete them. That are the overall options that we have. Keeping is typically preferable. The fact that some information is missing, the fact that some customer did not give his age, while another customer gave his age, that could be important. It could tell you something. If you're a marketing type of analyst, let's imagine a marketing type of setting, it could tell you something about the customer's willingness to share information, but also about the customer's willingness to share information with your company. So that might be important. Quite often, the fact that some variable is missing can be important, and this is why you want to keep it typically. By the way, there are algorithms such as the decision trees you learned about last week, which can easily cope with missing values and don't even require some treatment. Not treating them, but putting them into an algorithm that can process missing values might not always be the best idea, but it's clearly possible with some algorithms, such as trees, which is one of the nice features of decision trees. Other models, other techniques, regression type techniques, they will not be able to process this missing information. So that was keep. Delete should typically be avoided if you have a data set where the number of the number of observations is so large that you feel, okay, I have some information where a value is missing. I don't care. Sometimes deletion is a viable strategy. And if we keep them, commonly we will use some way of imputing the missing value or replacing it. Strictly, imputation and replacement are 2 different things. These terms are sometimes used interchangeably, though. But strictly, they are not. Replacement means that we find some alternative value. In a simple case, the missing value, the age value the customer did not give, we just plug in the average age. Or maybe better, we use the median age as a replacement. As a little thought exercise, answer for yourself why it might be better to use the median as a replacement compared to the mean. And for nominal attributes, we could use the mode as the most frequent category. That's simple. It clearly introduces artifacts. We put in some value which was not the true value, but it is a workable way, a simple way, a workable way, and an often pursued strategy to handle missing values, replacement. Imputation is more complicated. We can build a little mini model and try to predict the piece of missing information. Let's stay within the picture of this example, a customer did not give his age. So we miss a value for age for this single customer. Why not building a regression model that uses age as the dependent variable and all the other covariates that he has access to predict the age, and then using this regression model, we impute the value, the missing age value for this single customer or this bunch of customer. That's possible. Be it a regression type of technique. In fact, we can use any type of technique. Tree-based algorithms, nearest neighbor-based approaches are popular here as well. There are some papers using Markov chain Monte Carlo methods. But it all comes down to building a mini model. And this mini model, well, we can estimate it from using the entirety of data that we've got, meaning from all the customers where the age is available, where age is then our dependent variable, or we can build these models if we have enough data, taking into account group membership. So say we are trying to predict an age value in a credit scoring data set where there is a target variable, good, bad, and then if we know that for the customer where the age is missing, the label was bad, we could build our mini model only from the bad customers. There are some, variants on how we can execute this strategy. It's good practice typically if you do either replacement or imputation. So you put in some age value to remedy the missing. It's good practice to add a column called a dummy column, dummy variable, which is either 0 or 1. And you put a 1 whenever you impute some missing value for age. So this dummy could be, was age imputed? ? And then you put 1 if yes and 0 if not. This way, your learning algorithm to be used later has a way to interpret the imputed age value as an age value which is somehow different from the others, provided the learning algorithm is able to relate these two pieces of information. Well, a more fundamental question is, in terms of deciding on a replacement strategy or on a missing value strategy, whether the data is really missing at random. In many cases, it is not. And this would basically rule out, or should rule out, simple strategies like mean replacement. But let's not overcomplicate things here. For missing values, some easy strategies now have been covered. How about outliers? Unusual observations, but actual observations. And they are more difficult to handle. First of all, we need to decide how we can detect them. But this we basically already discussed. Plots like the histogram, as shown here, or the box plot are obvious ways to identify univariate outliers, right? Or you could also look at statistics. The formula you see here, that's the Z-score. It's a well-known transformation in statistics to standardize variables. You have a value xi. X could be age again. And I is a single observation, single customer. You subtract the mean. You divide by the standard deviation. And this gives you a Z-score for age for that customer, which has certain properties if we believe that the age values or the raw variable followed a normal distribution, which is typically not the worst assumption, right? Then, for instance, we would be able to tell how Z-scores of an absolute value larger than 3 are very unlikely. And relating that then to the normal distribution, we can translate that into crisp probabilities. So a Z-score less than -3 or above 3 is typically considered an indication that this variable is an outlier. And if you compare this Z-score type method, which you could also implement using the interquartile range, by the way, if you compare that method to the histogram, then they both have pros and cons. Histogram is more informative, but geared to a single variable. these z-scores, you can quite easily construct them for many variables. And then, let's say for 10 variables, you do this set transformation for each of the 10 variables. Let's say we have 10 variables here, so we have, where's my pen? We have x1, we have x2, all the way up to x10 in our table. I imagine that to be my data table, right? We translate all the values into their z-scores. So after the transformation, all these x values have been standardized, and let's say we have loads of these. We could look at the maximum, and let's assume, well, I'm lacking some space here, but let me clean this up. So let's say we look at the maximum of the absolute value of x, of our variables. And we tabulate this, we create this table in this manner. Then the maximum standardized value of x1 that we find here, we can compare that to our threshold. So we can ask, is that greater than 3 question mark? And for x2, how is it there? Is it greater than 3 question mark? And so on. And this way, we can immediately identify those variables, those x1 or x2, that are vulnerable or that appear to be affected by outliers. And that helps us to also conclude that some variables are unaffected by outliers, and then we can focus our attention to those variables that are affected, and then use techniques like the box plot or the histogram maybe in order to check more carefully, right, what's going on here with this variable, what's going on in x1, and do I need to take some action? That's a useful way to combine graphical and non-graphical approaches in order to identify outliers. And if you have a large data set with many variables, graphical approaches break down. So you want to use some statistics beforehand to target your effort to those variables that are most effective. Okay, just as a little note, I did think about outlier only in a univariate sense. I was thinking about one variable, age, and then discussing how in this variable we are able to detect outliers. And this is a bit simplistic. We could also think about outliers in a multivariate sense. Here we have age and salary, and I highlighted 2 outliers in this plot. And well, the story here is, if you agree, for example, that this data point, if you agree that we consider this data point an outlier, then the story to tell is that you would not see this outlier in a univariate sense. Think about that. Univariate means you project all the points to one axis. So you for example, you could project all the points down to the age axis. All point goes down to here. Then this single age values that we just established as an outlier would not appear unusually large, probably. Same story if we move them to the other axis. The point emerges as an outlier only if we look at the multivariate perspective of age times salary. But that theoretically, that's perfectly sound argumentation. Practically, if we consider the step of dealing with outliers, well, there might not be enough time in an analytics process or project in order to, well, address outliers with this degree of sophistication, worrying about multivariate outliers, and then the equivalent to the z-score could be something like calculating the Mahalanobis distance, where we consider the mean vector or the vector of the means and the covariance matrix, and then compare using this metric the distance of data points and identify outliers by calculating that for every data point and sorting them to check which are the ones most dissimilar from the central points of the distribution, accounting for the covariance, and then flagging these points as outliers or examining them in more detail. That's quite complicated. So it's good to be aware of that. But in many projects, you might need to target your efforts. Oh, sorry for that. To other tasks. There are many other tasks than multivariate outliers analysis. Okay, that was outlier identification. Now we know which cases are problematic and how do we treat them. If we decided to take action, then what is typically done is to apply some truncation scheme. And this is nicely shown here, I believe. We could just truncate any lower or upper outlier. Note these blue points. Here we have a lower outlier, here we have an upper one. And we basically change their value. We manipulate the data. We project their values to some cut point. For numeric data, we might assume it's normally distributed and then say, okay, well, the mean plus 3 times the standard deviation is the largest possible value. So the z-score of 3 is the largest value I'm willing to accept. Or you can apply the same approach, but instead of doing it parametrically, you just use the box plot approach and do the truncation based on the interquartile range, which is more robust than that score. So you basically project the value of every outlier to that of your cut point. So for an upper outlier, let's say, you project basically to let's note that down. So let's say we have an upper outlier, some very large h value, and then basically we replace that with Q3 of h. Well, this notation is meant to say so the third quartile of the h distribution plus, and said it's an upper outlier, so plus 1.5 times the interquartile range. That would basically be our equivalent, how we replace or adjust upper outliers using the interquartile method. There are some other schemes, but I believe this interquartile range-based approach is quite useful if, and that's the big if here, you decided to adjust outlier values. If you want, well, why is that a big if? For example, if you use a decision tree type of analytical model in a subsequent stage, you probably don't need to worry about outliers. Think about the tree learning approach and how trees are grown. They are entirely robust toward outliers, so there is no need to address them. Different story for regression type techniques, network type techniques. There, it does make sense to consider adjusting outliers to avoid an overly large impact of a few observations on your model. What do you do next? Possibly, before in terms of transforming your data, readying it for analysis, you might want to scale it. Scaling means you change the value range. And again, that transformation that we just saw could be a way to scale your data, or else there is this min-max scaling, which you see illustrated here, which is just a simple linear transformation of your data such that after the transformation, every data point lives in a certain range. And with the min-max scaling in the way I'm illustrating it, if you think about it, this range will be 0 to 1. So 1 is the largest possible value and 0 is the least possible value. Check that out if you have a value like XO, your original value, O denotes original, and you subtract the minimum of the corresponding variable. Well, if this value X was the actual minimum, you obtain a 0. So this is how the smallest value possible here is 0. And if it was actually the maximum value, which is the other extreme, then you basically have written down here the max of xo minus the min over the max of xo minus the min. So this is how, whenever xo happens to be the maximum, the resulting value of this transformation gives you a 1, right? So with that, you scale your data to a certain interval, and you see on the right-hand slide how it does not change the tendency of the data. It's just a transformation that you apply in order to enhance the comparability across variables. Imagine here we have salary and years of education. Okay, let's say this is YOE. So I'll abbreviate that with YOE, and I'll abbreviate salary just with a capital S, let's say. So S is salary, and then let's assume so we have salary, we have years of education. Sorry, I just messed up my example. Imagine a regression model where we just predict some quantity y, whatever that is. This is where I messed it up, really. Sorry about that. But just imagine you have a regression model where you want to estimate some dependency between a variable y, a target variable y, and then you have beta rho plus beta 1 times s salary plus beta 2 times years of education. And you know by now, originally my idea was to have salary as a dependent variable, but then I can't make my point, which is, if you have these two variables in your regression model, S, salary, and years of education, Y or E, provided they have the same value range, you will, it will be a little bit easier to compare the regression coefficients. But when saying that, I only mean for the human. When we interpret things, we look at the beta, we look which is bigger, and that tells us something, which value is bigger, about the importance of the variables, how much they affect our dependent variable, if the data was scaled. If the data was not scaled, then the beta coefficient will embody two things. It will basically capture the strength of dependence between S and Y, but it will also address the different value ranges. And this will make it slightly more difficult to make comparison which variable is more important by the human. Statistically, scaling is not needed for regression type models. We do this for interpretation. There are, however, some statistical techniques like nearest neighbor methods, where if one variable like salary is measured at a much larger scale, like thousands of euros, than another variable, like years of education, then the larger variable might overshadow the impact of the smaller one, or the variable with smaller values. So it is possible that not scaling your data will adversely affect your statistical model, not with regression type techniques, but with other type of techniques, neural neighbor type of techniques, for example. So it's good practice to scale your data, which obviously applies to numeric variables. Something else you might consider is to discretize your numbers. So moving from a numeric variable age to, let's say, a categorical variable age cut with 3 levels, junior, middle-aged, and senior, for example. This discretization is debatable. It's debatable whether it makes sense, but it can be considered. It avoids the negative impact of outliers. So if you're ready to discretize all the numerical variables in your data set, no need to worry about outliers. It can increase comprehensibility for the human again. It may give you a way to capture non-linearities in the data with a linear model. And it might have some other advantages. The disadvantage is you lose information. You're no longer able to distinguish your customers with the same level of granularity. And then you might need to worry more about how you treat the actual categories in your model. More on that shortly. But it's clearly something that's often done with discretization. And here I'm showing why it might help you to capture nonlinearity. If you imagine a hypothetical correlation structure between a variable age and a variable default risk, how risky it is to lend to some client. Let's say larger values on the y-axis indicate higher default risks and are bad in that regard from the perspective of a financial institution. A linear model could only fit a straight line to this data, which would maybe then look like this, right? And it would overlook this bump in the data, which essentially says that young people are very risky to lend to, or very young people. Then, however, there is a segment of young people, not the youngest one, but still young, where lending is not so risky. But then there is yet another group of people aged above 26 to, well, maybe 35, whatever that value might be. This peak here, maybe it's 35. So it's a very odd pattern in the distribution of the young customers. And from there on, we see a trend which is quite typical in banking, namely that the risk of lending decreases with age, or in other words, youngsters are more risky customers than more senior people. But our linear model would not be able to pick that up. Whereas, if we discretize our data, then we obtain multiple age categories. And, well, essentially, you could imagine that you do not fit one line, but 3 lines to the data, which would nicely allow you to pick up this odd behavior. It's very stylized, this example. Don't over-interpret it, but it's meant to signal or give you an intuition how discretizing a variable might help you to address non-linear relationships like this one, even if you use a linear model. In terms of how you discretize, there are alternative approaches. For now, I consider an unsupervised one where we just use the variable. Let's say I want to discretize the variable salary with these 6 values. I don't use any other information. I could perform an equal interval or an equal frequency binning, such that, assuming I want to obtain 2 bins, 2 groups of salary, then by going for an equal interval approach, you see what will happen. Equal interval means that you have a salary width of equal length, for example, $500. And then your first interval will cover 1,000 to 1,500 income, and the incomes between 1,500 and 2,000 will be covered in the second bin. And you see how the bins are unevenly populated. So in the first one, we have 4 clients, while we have only 2 clients in the second bin. But the width of the bin is equal. And equal frequency binning is just the opposite of that. We have both bins equally populated, 3 customers in each. Each bin has 3 customers. Yet the range of values differ. Small for bin 1, just 1,000 to 1,300. Much larger for bin 2, 1,400 to 2,000. So it's twice as large. Here we have a range of 600, right? So 600 euros, whereas, oops, sorry, my fault. It's clearly not, it's not 600, that's 300. And here our value range is 600 euros or dollars, whatever that is. So this is the difference, and you want to know, and what is better, what is it that I should do? And unfortunately, I cannot tell you. It depends. It's very often this is the answer. If you believe that this binning has a big impact on your analytical model, you will need to try out these options empirically and see which one works better. One of the reasons why model assessment is important. More on that later on. Okay, so there are also ways to carry out the discretization in a supervised manner. See how I changed my setting. Now I have salary plus good and bad. And then I can fit a tree to that data. And if I fit a tree to that data, this tree will present me some split points, as we saw last week, using the known splitting criteria, information gain implemented with entropy or Gini, and the split points of the tree, 1400 and 1700 in my example, they would inform you how you can bin your data using the thresholds. And because the tree uses the target, that is a supervised approach. And if you constrain your tree to some maximum depth, you can immediately govern how many bins you want to obtain in the end. The maximum depth of the tree will determine how many splits are performed, and therefore it will determine how many bins you obtain in the end. All right. The same approach also works for regrouping. Once you discretize your data, or maybe you start from a category variable in the first place, check out this example. The variable is credit purpose with different levels. That's a nominal variable. Or it could be a variable that was originally numeric and has been discretized. Now we could basically examine whether we are able to further reduce the number of levels. From currently real estate, car, holiday, and study, we have 4 levels. Do we need all 4 levels, or can we maybe reduce that somehow? Again, we can try to fit a tree to that data, examine this tree, and then see whether it's possible to merge some category levels. As you will see, merging category levels and reducing the number of levels also simplifies your analysis. And the reason why that is the case is that once we move on to categories, once we talk about categories, original raw categories or numeric variables that have been discretized, we need to worry about how we put these into an analytical model, provided we use regression. And by regression, I would also consider nonlinear regression type of techniques like neural networks. Again, trees would not cause us any problem, but regression type of models, we need to code our categories. And we could code the categories by just numbering them. Car, category car, or the category level car might receive a 1 and 2 for house, etc. And there are numerous problems with that approach. It's just wrong. If you really try to think what this would imply, then you can convince yourself that doing it in that way, just numbering category levels, will introduce an arbitrary ordering into your data, which just is wrong. All right. Sorry about this little break. So the sequential numbering of categories is wrong, and the right way to do it, the common way that you have probably seen, would be to use dummy variables for each category level. Well, n-1 typically, where n denotes in my example the total number of levels. Otherwise, we create some linear dependency in our data. And this would be the way how we code our category levels in a regression model, we would have one category for the credit purpose car with a regression coefficient. Here it is. Another one for the category house. Here it is. And for travel and so forth. This shows us it's perfectly fine, this approach, don't get me wrong, but what we see here is that the more levels we have for a single category, the more of these dummy variables we need. And this approach can easily blow up our data set in terms of dimensionality. You may have heard about the curse of dimensionality. It's a well-known concept. We will look at it shortly in the next week or second to next week. Which, well, by the very name identifies high dimensionality is a problem for various reasons, so introducing so many dummy variables and thereby amplifying the dimensionality of our data set is a problem, potentially. Which raises the question whether there are better ways to do it, and in fact there are. And this is a surprisingly little known approach with weight of evidence coding, which I believe is really useful. The goal is you have one categorical variable and you want to encode it, but not using dummies that amplify dimensionality. You want to encode it with a single numeric variable. And you see the transformation, how it's constructed. It's based on the odds level. It's just the log of the odds level for a single category level. This is how to read the slide. I.e., consider a binary problem, good, bad. You see these labels. And for a single category level, let's say credit purpose equal to car, you count how many goods and bads do I observe among all the customers who lend money to buy a car. Find the ratio of these, you log it, whereby the log is just a scaling. It's not essential, not instrumental to the idea. And this odds level that you obtain is your replacement of the category level or the weight of evidence of that category. Well, just about this log transformation, if you think about this approach, and I'm plotting the weight of evidence as a function here of the frequency of bad customers in some category level. So just to make that a bit more intuitive, we could have e.g. Purpose, you know my example, credit purpose equal to car, right? This is what I meant by cut. And then we look at the frequency of the relative frequency of bad customers among those who lend money to buy a car. And if that is 0.5, then obviously the relative frequency of good customers is also 0.5 because they need to add up to 1. And we see how the weight of evidence, because of our log scaling, is then exactly 0. Right? So this is why we log the odds ratio. And then we can, by looking at the value, establish that whenever the weight of evidence is greater than 0, this category level, purpose equal to car for instance, is more associated with bad customers than with good customers. And the other way around. That's why we use the log. And in terms of implementing it, you find another example in the slide book here, which shows the calculation for a categorical variable age group with levels missing, 18 to 22, 23 to 26, etc. And we count the number of customers in these categories. In total, I have 2,000 customers in absolute terms, and then the relative frequencies corresponding to these counts. And then we distinguish between goods and bads. So you see how the 50 customers where age is missing, for example, how they basically split up into 42 goods and 8 bads. This is how to read the table. And then the 42 represent 2.33% of the overall 1,806 customers that are good. So out of the goods, 42 or 2.3% did not give an age value, or age is missing for these. And you see the corresponding calculation for the BADS that goes on. And for each of the rows, each of the category levels, you can basically find the ratio between P good and P bad. You log that, and this gives you a weight of evidence. And what you do with this is the weight of evidence that you obtain here, that is your replacement. You go through your data set, and for all the customers where you have age equal to missing, where you have a missing value of age, you just plug in the weight of evidence 57.28%, which is a number. And you proceed accordingly with the other category levels, and in this way you transform data transformation, your categorical variable with distinct levels into a numeric variable. That's the idea. And then you don't have any dummy variables anymore, which would increase your dimensionality. It's also exemplified here, and here on this slide you also see then the resulting hypothetical regression model, where we have only two variables, although originally we had amount and age as covariates, age with different levels. We would have needed a couple of dummy variables to code age, which would introduce more betas and raise dimensionality, but we avoided. We avoided that by using the weight of evidence transformation and would just use the weight of evidence column as opposed to the age column in our analytical model for our variable. There are some caveats to note here. If you have many category levels and one of them is associated only with goods or bads, then the calculation is strictly not possible, but there are ways around that. And there is a nice paper by Moyers and David Martins where they basically show how the weight of evidence approach is feasible and actually effective even for high cardinal categorical variables. So variables with many levels, like zip codes, for example. Zip code is a category. And think about how many zip codes you have in Germany, for instance, or elsewhere. Then using a dummy coding for a variable zip code would be infeasible. And just using a vanilla weight of evidence transformation is probably not the best idea, but it's a workable approach. So it's quite nice to be aware of that. There are some further problems, however. The weight of evidence might go extreme if there are no goods or no bads in a category. You remedy that with including some artificial data points to then have at least some few data points in the category. That is basically introduced in a paper by Sadrevsky. And another problem would be if new levels come up in your test data that you haven't seen in your training data. That's a more substantial problem, but on the other hand, what Moyers and Martins argue, let's say you have a new purpose for which somebody wants to lend money. Previously we had car and home and state and holiday. And now somebody wants just to lend money to have some cash. And you haven't seen cash as a category level in your training data. So you don't know how the category level cash impacts your risk. And then they say, Moyers and Martins, well, then the most reasonable value for the weight of evidence is 0. 0 means, well, good and bad is equally likely. I haven't seen this level before. I don't know anything about it. And that is a plausible replacement or way to address the fact that in the test data there might be some new category levels where you would then don't know the value of the weight of evidence. All right, so this transformation I think is important, is good to know. which brings me to the last slide of this talk. Let's sum up a little bit. We have looked into why we need data preparation and covered some techniques, some activities that you will find yourself busy with when working with real-world data. I would like to emphasize once more the importance of visualizations in the scope of EDA to get a good understanding of your data, which will then prove valuable for all subsequent modeling stages. EDA also helps you to identify missing values, and you have learned about ways to replace or impute them and what's the difference between the two, right? Same with outliers. And the last bit was a bit more specific: scaling and discretization for numerical variables, coding of categories, possibly with the weight of evidence approach. My hope is that by now you have a good set of tools available to massage data prior to throwing that onto a decision tree or a regression model or whatever type of model you consider. So that concludes chapter 4. Up next, we will talk about the evaluation of predictive models and look into some of the performance indicators and experimental designs that you can use to assess whether a predictive model is of high quality. So, thank you very much for your attention, and I look forward to see you in our next lecture on the 20th of November.